Nice.
So after the notebooks and me not learning Chinese, in the meantime to get Acrobat full screen, let's get started. Zvonko Kaiser from NVIDIA. If you've seen my keynote, the title is Kata and Confidential Containers with GPUs. Just to set the term straight, so confidential containers is an umbrella term for Kata plus some S components. So who is familiar with Kata? Okay, we have some Kata folks. Who is familiar with confidential compute? Okay, do I need to explain confidential compute just shortly for the others? Yeah? Okay. Just shortly. Right, we have the host, we have the kernel, we have the hypervisor, and then we have the VMs. With Kata, the threat model is that we do not trust the workload, so that's why we are packing them into VMs, so that a malicious workload has no access to the infrastructure. Right? With confidential compute, this threat model changes completely. It's the other way around, where the workload does not trust the infrastructure. Right? With Kata, the complete infrastructure, any CSP has access to your VM data. Right? Can do snapshots of your memory, can do snapshots, can inspect the memory. Nothing is protected from the CSP. With Kata, the confidential compute is the complete VM is encrypted with a security processor on the CPU, so that the infrastructure has no access to it. There are more things around that you need attestation. That you, for example, attestation is the process of proving that your state that you're expecting is really the state that you are measuring on your kernel. So that you can prove that the VM that you're spinning up is in a state that you're expecting. Right? So this is just the main thing about the confidential compute. But today I want to talk to you about confidential containers and a little bit of background, the agenda, road to confidential containers, the NVIDIA enablement stack, what we have done to create the lift and shift properties with confidential containers, why we have chosen Kata, a little bit about the virtualization reference architecture, because we have some sophisticated use cases that we want to enable. So I'm going to explain what we've done that, and then a short summary on confidential containers. As you all know, containers is just a change root on steroids, right? With some namespaces from the kernel. It's not really protection, it's more a delivery mechanism of software, and we have this weak security boundary between the runtime and the host operating system. And containers, nothing else. It's a modern way of packaging, sharing, deploying applications. It abstracts only the user space. There are things like SLinux, AppArmor to create more guards around the container, but that's not really something that's protecting us. So we need hardware isolation, and host changes can easily break the containers, because containers are still sharing the very same host kernel. And a container breakout can take over your node, can take over your complete cluster availability. So I think if you attended the other Kata talks, everybody is saying the very same thing right now, what I'm saying, that you just cannot trust containers. In the past, there were more sandbox environments that are tried to fortify the isolation between the container runtime and host operating system. Right? We have unikernels, we had Nabla containers, if somebody remembered this from IBM. We have gvisor. We have Qbert are fat virtual machines, right? Full-blown operating systems in a container. The container is just a delivery mechanism. We also have things like Firecracker, but our focus was always in the past, and now Kata, because they're just the micro-light virtual machines that we're using. Yeah, I don't have to go too much into detail what Kata is, but the main advantages of Kata is that they're supporting a broad spectrum of hypervisors. You can run untrusted code in a container, which is the threat model of we don't want to trust the workload, we want to protect the infrastructure. And Kata is fully OCI compliant. fits into the cloud-native space without any code modifications. Right. There are other sandbox environments that were suggested to protect the container, like homomorphic encryption, secure multi-party computation, federated learning. But those are niche, powerful, but oftentimes 1,000 times slower for deep learning or for practical AI solutions. Well, and one thing I want to emphasize is that TEs is not really something new. The first TE appeared around 2004, and if you have a phone, you're running TEs for a long time. All your Apple Pay, Alipay is all running on a trusted execution environment. But today we have a lot of trusted execution environments like SMP, TDX, and CCA coming up that can support proper VM isolation with confidential compute. Okay, little excursion to the NVIDIA enablement stack with containers. It's essentially pretty easy how GPUs are enabled in containers. Before it was a pre-start hook, but now we have CDI. CDI is the container device interface, which provides specific files, binaries, libraries from the host into the container. And some of those is like, for example, /dev NVIDIA or the NVML with CUDA stuffs that are provided into the container, which is needed because there's a hard dependency between user space and kernel space with the NVIDIA drivers. So you always need to make sure that the drivers that you have installed are fitting the user space. If we are extending it to Kubernetes, where we have the GPU operator, it deploys a lot of other components that we need in the Kubernetes space, feature discovery, labeling your node, which is capable of running GPU workloads. Then GPU feature discovery exposes more features if you have a driver loaded, CSI networking, and all the other stuff that you need for GPU networking is provided with a GPU operator. So we have the low-level enablement with CDI and the pre-start hooks to make the GPUs available, and then on the Kubernetes level we have the GPU operator providing all the needed bits and pieces to enable the GPU properly. Right? To make this lift and shift with GPU containers also in Kata, we just took this pattern that we have already on bare metal and just put it into the VM, right? So that the container that's running in Kata will feel and behave the very same as you're running on bare metal. So there are no excuses, there are no surprises on that one. We are supporting PF and VF pass-through, right, where container D takes care of the PF pass-through, but then inside we are doing some handling of the GPU to properly provide it to the container. Which means no modifications exist in GPU containers, and we can support different runtime configuration per container. For example, you could have one container that runs with a PF pass-through, you have another container that runs with VFs, then another container that supports, for example, GPU direct RDMA, or another container. So you can change the PCI Express topology per pod, per workload, if you need it. Just to reiterate why Kata containers are now kernel and user space independent, meaning host changes cannot break our stack because we heavily rely on the guest kernel and the drivers. They are kernel changes can break the NVIDIA stack, so Kata gives us a nice isolation to protect it from kernel and user space changes on the host. And seamlessly plugs into container, runtimes, into Kubernetes. As I said, we are kernel and user space independent. And we can run untrusted code in a container. Virtualization is the second line of defense. I'm not saying that's 100%. There are still breakouts out of the VM. And if you're just looking at Kata, if you break out of a VM, you can still attack the other VMs because they're not encrypted. With confidential compute, you can still break out of the VM, but the VMs are encrypted, so you cannot eavesdrop on the data of the other people. Or tenants that if you're running on the same host. How? Yeah, we are working with a lot of companies, especially here with the guys at Ant Group, and with IBM, Red Hat, to create reference architectures upstream and build the runtime classes that we need. And we also extending our cloud-native stack to run any sandbox environment, be it Kaiser, Kubernetes, Kata, confidential containers. It should feel the very same for any of those sandbox environments if you're using a GPU. Yeah, I already explained what we're doing. Yeah, one thing that I explained before is the virtualization reference architecture. Let me just time check. Yeah, wait a minute. So those are essentially the use cases that we want to enable with Kata and confidential containers, right? Be it a GPU or you have a NIC, if it's MIG or time sliced or MIG backed. The problem with, or the complexity with those use cases is that if you don't have the proper PCI Express topology in your VM, the driver will just deny doing, for example, peer-to-peer with a NIC. So just say, okay, no, that's not a proper PCI topology. I'm not going to do any communication with that. And there are things like IOMMU, ACS, ATS, if you're using PCI root port, switch port, etc. So it just gets complicated with the GPU. And then you have hardware constraints, then NUMA, socket affinity, etc. There are essentially two modus operandi to solve that, that are used in the past. For example, if this is our host PCI Express topology that we're looking at, right? We have a Mellanox NIC and we have a GPU under a switch port on two NUMA nodes. Usually what CSPs are doing, like Azure, they're just flattening the hierarchy, right? But then you're losing all the information, which GPU belongs to which Mellanox NIC, and most of the time side channels are provided in the form of topologies XML for upper level libraries like Nickel or IB. But the problem is some of those InfiniBand or Rocky workloads do not understand those side channels like topologies XML, and low-level software like IBRDMA and UBERS or GDS has no idea how my PCI topology looks like and what and how to enable. Right? So this is flattening, but then you need a side channel, and that's what we can enable per default in Kata. Right? You can hot plug to a root port, or you can cold plug to a root port. Again, independent or per pod, you can decide if you want a hot or cold plug. Another thing that we can do is there is a specific PCI Express capabilities setting in the PCI Express space where you can add additional information for the GPU and providing a click ID, meaning you can provide the ID which of the GPU and the Mellanox NIC are belonging together, and then QEMU will set up the peer-to-peer capabilities between those two devices. What we were thinking, but how are we going to provide this information transparently in a cloud-native way, right? For if you're running Kubernetes, and CDI is one thing that we took, which is the container device interface, where you can provide meta information to your Kata pod, saying like this GPU 0 with PDF 41 belongs to this Mellanox NIC, and this is the click ID, the group that we are using for peer-to-peer communication. So you can provide meta information to your Kata confidential containers pod to provide the correct mapping between the GPU and the NIC. The next mode that we added is host topology replication. Right? If you have this topology on your host, let's just replicate it inside of the VM, and then the driver does not have to need to figure out what's the correct topology. So we are leveraging several libraries on the host to see what the host topology is. We are doing some kind of host topology detection and replication then in the VM. And if you enable it, the setting is in Kata. Let me just see. Oh yeah, it's the switch port. If you know that you have switch ports, the result would be a switch port in the VM. And we are also adding the ACS settings and the ATS settings so that you have proper peer-to-peer communication between GPU and NIC or between two GPUs. Right? So we have both modi. Either you flatten the hierarchy because you say you don't care about the hierarchy because I'm just using the GPU, or you can say, oh, I want a host topology replication because I'm doing peer-to-peer or GPU direct RDMA, stuff like that. So both modi are supported in Kata virtual containers. Of course, we have hypervisor resource limits. We cannot attach as many devices as we want, like 32 slots on the PCI pod bus, 256 slots for a complete hierarchy. This is the example for QEMU. We can only have 16 root or 16 switch ports. And before 6.4, without IO-MMUFD, it meant always you need to provide a complete IO-MMU group. Some devices, like the GeForce, have also audio devices attached and USB devices attached, etc., etc. So this whole IO-MMU group needs to be in the VM. But you don't want to map all those devices as well to a PCI root port. So what we also did is that you can say, let me just see, that you can say, for example, per CDI, you can say, oh, put the NVIDIA devices on the root port because I want to have high-speed connections there, and just put the Mellanox devices that were in the same IO-MM group on a PCI rich port, right? I just don't care about the other devices that are needed for IO-MM group. So you can decide how and when you're going to attach all those devices. So this is in short, the virtualization reference architecture. We have an extensive document on that. We are adding currently NUMA support for Kata to even have more and better coverage of all the uses that we're using in the GPU use case. Let me just see, what's the time? We have 40 minutes, 8 minutes. Yes?
There is no talk after this one.
Okay,
so
yeah.
Chill, take your time.
Chill, yeah.
Take your time.
Take your time, yeah. That's right. Explained all the Kata stuff, and I said before, confidential containers is just an umbrella term for Kata plus some guest components, which means we can use the very same functionality that we use for Kata to enable confidential containers. Again, the same mechanics inside of the VM, nothing changes. It's a seamless transition from Kata to confidential containers. Nothing changes. The only thing that changes is the pod RuntimeClass definition that you're doing on your manifest, right? For bare metal, without any, just add Kata or CC for confidential containers. And then on a Kubernetes cluster with the GPU operator and all the other stuff that we have in the state, you can run like the bare metal containers, on some of the nodes. Then you can run Kata containers or confidential containers on the other node. And then, again, as I said, per pod you can change PCI Express topologies and run, for example, GPUs with VF here, or run a KubeVirt VM on the same cluster. So it's completely up to you. What we're doing is, if you have a confidential cluster, confidential node, you're not doing any heterogeneous work there. You just allocate specific cluster, specific nodes just for confidential compute and the other one. But technically it's possible even to run all of those combinations in one cluster. Right, as I said before, attestation is a big part, proving that the current state is the state that you're expecting with some reference values. We are following the REDS architecture. Then the GPU has all those components also implemented. And we currently added support for composite attestation with the GPU and the CPU. But there's more work to be done. One use case, we can switch that. One use case that is important in confidential compute is the secret key release. Right? Once you start up your workload and attest it that the workload is what we're expecting and the hardware is in the state that you're expecting, the CPU is in the state that you're expecting, you want to release secrets into your VM so that the VM, for example, can load encrypted storage or decrypt your data or decrypt the model that you put into your VM to do, let's say, training or inferencing or whatever you need. Right, that's what I mentioned before. So there are several implementations on how you can implement attestation. GPU is one of the first accelerators coming into a confidential environment, but as you can imagine, more and more devices like a NIC, like a DPU, are going to be part of your TCB or trusted compute based in a VM, and those need to be also attested. So we are working hard with the community to see how we are properly going to attest all those devices, because depending on when you're doing this and how you're doing this, you may introduce timing attacks, because some device is not yet ready, or one device is ready, can do DMAs, and this device could DMA to the other device, overwriting things, firmware, whatever, right? So we're thinking of a proper way of how to attesting all those components inside of your VM. Also another topic that we're looking at, of course, not only attestation of the hardware, but also of software that's running, runtime integrity of your guest file system, of your container images, and other components that you may need in user space should also be measured and always attested. That's trusted storage. Yeah, trusted storage. We need trusted storage for our workloads. And this is just some notes on my side. So if you're thinking about AI and ML as a service, usually you have several personas that are involved. And one of the use cases that we're currently thinking of is the data clean room. How do you have a data owner, model owner, and infrastructure owner in the very same VM and attest each other against each other? So how can you trust the data owner and the model owner and the infrastructure owner in the very same VM? And then you have the clients who want to consume this workload, and how do you protect your VM against malicious clients that want to exfilter data, exfilter your models, etc. And there are essentially three main stages of an AI ML pipeline. You have data exploration, right? The data owner wants to protect data from being leaked. Then you have the model training, and again, data owner wants to protect the data from being leaked. After the model is done, the IP protection, right, of those foundational models is a central risk. So if somebody leaks some models on confidential data, it can create a lot of risk, right? And then we have inferencing. Trained model should not be leaked or tampered with, and client data should not be exposed. Yeah. My go-to example is like the hospital wants to do check trace from patients, which is the client, for diseases on trained model from another institution, right? Because the hospital may not have the capabilities to do the training. They want to buy a model, then use their data and provide maybe to some third party, to the insurance, whatever else, who is doing the operation. So all of those things need to be protected against each other. We've seen, talked about homomorphic, secure multi-party, copy model, Right. Last but not least, let's say H100, a very old screenshot running in a confidential environment with confidential containers. Any questions?
So we are currently doing GPU attestation in some sort of like delegated fashion, right? So we're doing first CPU attestation and checking that our software works as it's intended to work.
Yeah.
And the software includes reference values for the GPU, and then we trust the software to correctly attest the GPU.
Yeah.
But what I understand is like TDISP is the future of GPU attestation.
Yeah.
So how would this look like in the end state?
Anyone heard about TDISP? Any PCI Express experts here? You heard? Yeah. Ant group does not count. So currently how the GPU works is with confidential, those private pages are not accessible by the GPU. What the GPU and CPU does is they're creating a public space called bounce buffers, where there's some key exchange going on the SPDM level between the GPU and the CPU, where they're doing a Diffie-Hellman exchange, so that the GPU inside here can create an encrypted buffer into public pages, and then the CPU on the host can copy out those pages. So there is a way on how to do it with bounce buffers today, and that's how the H100 kernel works. But with TDISP, we don't need the bounce buffer anymore. Everything is happening on the PCI Express bus. So the PCI Express bus, PCI Generation 6 will have all the capabilities to encrypt and integrity protect the PCI bus. All the packets that are going over the PCI Express bus are encrypted and integrity protected, meaning signed, encrypted, so that you can verify what's going on. With TDISP, you still need the user space component, the TSM, which is doing the attestation and giving the attestation to the outer, let's say, to NVIDIA remote attestation services or Verizon or ITA. So you still have the user space component that we currently have, right? Where we have the attestation agent inside the VM, and which is responsible for measuring the state of. So it will be just an extension of the attestation agent. But there are TDISP timing attacks depending on how you're doing the attestation. So that's a bit picky and complex.
So in summary, I still need to, like the Diffie-Hellman exchange happens on the kernel level, and I don't see that. But
you don't see that.
Afterwards, I can still attest it, and then I know what to trust this exchange.
Yeah. So this one is just pushed into the PCI Express level. You don't see it anymore. It's on PCI Express level, right? All the key exchange and all the integrity and all their stuff. Thanks. Yes?
I have one question. Are you already, or will you support partitioning of CPUs, GPUs in this layer? So if you have one, you can, I think there is some method currently that you can split it down and have different containers work on parts of the
So the buzzword is MIG.
Yes.
Right?
Yes.
We cannot do vGPU time slice. This makes no sense because it's context, right? So we need MIG. So we need real hardware partitioning where the GPU is sliced into hardware and you have guaranteed quality of service. So you have compute cores here, that's not shared. Memory is properly also divided for each of those partitions, and for confidential compute, it's very easy. It's called SMIC, which is secure. So. But it's not generally available. We are working on it. Yeah. Yes.
Are there any design documents of how you're doing the optimization of the PCI topology inside the guest, or like what you should be doing to do that optimization?
Yeah.
Asking you because I want to know that, and we don't know. I mean, that was wanting to do it for a while, but you've obviously done a lot of the learning here in Canada.
Yeah. Search for. It's Kata. It's in our GitHub repository. I don't recall the correct path, but it's kata-vra.md. You find it. Yeah, we are doing the updates on the NUMA topology. So once I'm back from the conference, I need to work with this guy, and then we are pushing NUMA topology into Kata.
Yeah. Sorry, we've been discussing this in the Nova community for a while, like how do we actually do that properly?
About 6 years.
Yeah, we have another document.
We've done it manually, but it's the automated.
Yeah, man. Yeah, essentially, if you follow like some of the patterns, I would even say do host topology replication.
That's my preference. Yeah,
Right.
so we've done that manually, but not automated it in Nova.
Yeah,
so
yeah.
it's good to confirm it's.
But it would be good if you know, because we're still looking for a proper tool to do the host topology detection.
Right.
Right? So I don't want to see that we have like gazillion tools to do that.
Yeah, I agree.
Right? So it would be good if we had like one tool, because it's still the same. It's the same queue, it's the same queue.
Yeah.
And any VMM can use it. right? Independent of QEMU, if there's this specific channel, because yeah, you just need to think about how to do it. Yeah, so this is this one, and then I'm also going to publish a performance guide for QEMU-based GPU direct RDMA GTS cases. Like all the SES settings, ATS settings, CPU pinning, and all the other stuff that you normally do, right? But there are some other minor things. Let me just think. There are some that you need to be aware of.
A very NVIDIA-specific question. Someone's trying to do a full pass-through of H200.
Yeah.
One of the issues you hit with that is, by default, QEMU can't map that much VRAM. Have you decided trying to address that problem? Because it's fixable, but it's just that it's not allocating enough memory address space for doing the mapping in one chunk. And the folks I've talked to, when they tried to do the full pass-through with their entire device, they were saying they're getting as good a performance with their CPUs instead of using the GPU with that much performance by having a now memory window. So that's something that's coming up from the Kata side of like taking an entire H200 or something of that class and using
Not really. Because one thing that the H100 does is bar zero decoupling, right? You don't in the CC mode you don't even have access to the box.
Okay.
You don't see it. The performance with the old VF-IO groups implementation is very, very slow. It got better with IO-MMUFD.
Okay.
So it's cut down by at least, my feeling is like at least 50 to 80% cut down of boot up time, because there's some parallelity there. So.
Yeah, so what's actually missing on the QEMU side is just very unified navigation now. MIXs up front to connect.
Yeah, with OVMF we need the IOM picture completely exposed. Yeah, that's
Yeah. So there's no ability to do that right now.
Oh, okay.
So if you read that video docs, they always say pass these extra command line arguments. We need to talk to the other teams to tell them that we need to be able to do that.
Yeah, you need, otherwise it will not boot. OVMF, you need the IOM picture completely.
So it boots, but it's incredibly slow.
It is, yeah. Well, in the CC case, it won't even boot if you don't set the aperture in OVMF.
Yeah.
Right. If we have default C BIOS, that's another thing.
So far we've got away with it because people have been having that, and you've got a subdivision of it, but it's going to be more and more of a problem as these GPUs start getting natural language.
Yeah, I plan to. Well, we this is like 3 years old, right? I've been talking about this, but not at the open infra before. But this is like 3 years old, and we want to upstream everything so that people can replicate it. And it's a reference architecture, right? So we want to have people replicate it on other systems. And I'm also looking into how we can not marry, but have better interoperability between OpenStack and Kata. Because, as I said in the keynote, you have different deployment modes, right? You won't always have a bare metal deployment. You may have VM as a service, right? CSPs like. Yeah. And what we don't want to do, this is what Fabian and the other folks talked about yesterday, how good are we, or how far are we from running on CSPs? Because we don't want to have any L1, L2, right? We want a L1. And if see some old folks here, they remember Zen with the .0, and
exactly.
Right? You have the primary VM, and you have the secondary VM, and this pattern can be repeated as well, right? So if we have OpenStack, and OpenStack creates us a Kubernetes worker, right, or control plane, and then a worker. What I would like to see on the L1 level that we can, spin up a Kata pod on the very same level.
Oh, okay.
Right? Not a worker where you do nested word, because we don't want to have nested word. We want to have everything on L1.
Yeah.
So you have again your primary VMs, right? And then you have your secondary VMs on the same level.
It's a bit like that CAA adapter thing. Because spoken about.
but right, the CAA, you have CAA here, right? That's the interface talking to the VM as a service, right? But VM as a service could be a CSP, could be OpenStack, or OpenStack is a VM as a service, right?
Yeah.
And then exchange CAA with launch layer, and launch layer could be everything.
Yeah.
Right, so the launch layer could be directly talking, and then you could do on-prem VM as a service.
Yeah.
You don't need to do CSPs, but you could do also on-prem.
This is explicitly what I would like to do. So it's awesome.
Then sync up and
we have to talk.
yeah. So that's the thing that I'm imagining with Kata. If you have not concentrating on cloud, I don't care, but let's call it launch layer or something else, where you can do really bare metal VM as a service. Because then what you can enable is you have then one interface. So if you have VM as a service, just run Kata. If you have VM as a service, you still run Kata, but you have this launch layer thing that says, okay, I can do my bare metal deployment of VM as a service. On L1, we don't do L2. We don't want to see L2. And then the nice thing is about this approach is that you can isolate your Kubernetes control plane in a VM, you're isolating your worker in a VM, and your Kata pod, the workload, is also completely isolated as a VM. And then if you say, okay, it's Kata, let's do CC, then you have encrypted VMs here for your worker, for the control plane, and for your workload. And then you can attest your Kubernetes control plane, your Kubernetes worker, and your pod, and the complete stack is attested. And then OpenStack could have something like a out-of-band, let's say DPU.
Yeah.
You plug in, which is your root of trust, which is not accessible by any of those hosts. And then you could do, let's say, a KBS that gives you the keys upon successful attestation of your VMs. Right? So there are a lot of things that you can do. But this would be something that I'm thinking about.
Yeah, it could. It's really good. I mean, there's obviously like stock interfaces that know that we're exposed to reuse the components from Kata, so we're not reinventing the wheels here. So it sounds good.
What interface? Well, we saw in the CCs for confidential compute.
It's not ideal.
I'm a little bit not concerned, but it's not the right thing.
Yeah.
You know, it's not like a mutually attested TLS connection. Yeah. And then you always need to have the port, and there's some discovery behind it. So you have to think about that.
Yeah. Cool.
Almost 25 minutes past.
Lunch?
Lunch?
Someone did it, right?